The Technical Training Department of Yaskawa America Incorporated presents Variable Frequency Drive Basics. Have you ever thought about what goes on inside a variable frequency drive? After all, when you stop and think about it, these mysterious boxes are really pretty remarkable. They help us save energy, reduce maintenance on our machines, and they give us nearly infinite control over almost any type of process powered by a three-phase AC motor. So how exactly do variable frequency drives, or VFDs, work? And what do you need to know about them? I'm Steve Kaler. Welcome to the second video of our two-part series on motors and drives. In part 1, you were introduced to the basics of three-phase AC electrical motors. Today, we are going to look at the basics of VFDs, or variable frequency drives. You may also know them as adjustable speed drives, adjustable frequency drives, AC drives, and inverters. Whatever you call them, what's important is what goes on inside of them and how we use them to control and monitor electric motors. In this presentation, before we look inside of a drive, we'll start with the many applications for variable speed drives, both industrial and commercial. We'll look at other starting methods, ways to start a motor that don't utilize a drive, and next we'll talk about the purpose of variable speed drives, why do we use them. We'll then walk through the typical layout and construction of a drive, and explain the components that make up this device. We'll look at different types of enclosures, and then, to wrap things up, we'll review this presentation with a few questions. Now, before we look at the inner workings of a drive, let's examine the applications that could benefit from a drive. Industrial applications often require very precise control. In the past, these applications relied on complicated gearing and clutches to control the speed of a given system. Examples would include conveyors, cranes and hoists, presses, winders and unwinders, high-speed machining applications, as well as many others. Now, in the commercial market, we are normally trying to achieve a given flow and pressure. This changes depending on the demand at any given time. Fans use inlet guide vanes, bypass dampers, or outlet dampers for flow control. Pumps use discharge valves or bypass valves to regulate pressure. Cooling towers would use a mixture of the two. Using a variable frequency drive for these types of industrial and commercial applications allows us to remove mechanical speed, flow, and pressure control systems that may prove difficult to regulate and could possibly be failure points. Instead, the drive easily adjusts speed and torque to given system demands. Now, on top of that, some variable torque commercial applications can take advantage of affinity laws and use the least amount of energy to meet the given flow or pressure demand. This can lead to energy savings that can have the drive system paying for itself within a short period of time. As we explained in Motor Basics, three-phase induction motors, when applied across the line, run in a narrow speed range, depending on load and motor characteristics. On their own, they're either on or off. However, motor drive systems are often incorporated to allow the system to operate at a wide range of speeds, while still producing full load torque if needed. The simplest form of control is a manual motor starter, which is nothing more than a means to manually open and close the contacts to start and stop the motor. Manual motor starters usually include some type of motor overload protection. A magnetic motor starter is similar to a manual starter, except you can remotely toggle a magnetic coil to bring in the contacts as needed. A drawback to both manual and magnetic motor starters is that they do not reduce the inrush current that the system will experience at startup. Primary resistor starting uses resistors to reduce the voltage going to the motor. After a given time, the resistors are bypassed and full voltage is then applied to the motor. These resistors will get hot and have a limited duty cycle. In other words, a limited number of start-stops in a given period applies. With auto transformer starting, we are tapping the transformer at different points, resulting in a change in voltage. After the motor is started, the transformer is bypassed. With Y delta starting, we connect the motor at start in a Y configuration, which exposes each coil to a lower voltage, then switches over to delta while the motor is in the running state. SCR, or thyristor control. The solid-state device is controlled to pass only a portion of the voltage waveform to the motor. These offer a smooth start to the given system and limit the current draw by the motor. When the motor is up to full speed, the unit then bypasses the soft start function and full voltage is applied. These units have limited start allowances for a given time period, but offer smooth starts instead of the stepped previous methods. So that brings us to the purpose of variable frequency drives. Here are some of the major capabilities a drive provides. If you viewed the Motor Basics presentation, you saw this diagram showing an induction motor's relationship between speed and torque. By adding a drive to the system, we have the ability to alter the speed-torque curve. This lets us take advantage of the motor's characteristics at multiple speeds, instead of being limited to only 60 Hz. VFDs allow us to match the speed of the motor-driven equipment to the load requirement. Operating a motor with a VFD provides full torque capability over a wide range of frequencies. Having full torque available allows us to use a standard or general-purpose motor in many more applications and situations than we would otherwise be able to. Furthermore, we can limit the output torque of a motor for a given application or point in the process should it be required. Since we now can control the motor, we can program our own acceleration and deceleration, or accel and decel times. Now this will vary depending on the application. For example, a fan can utilize longer accel and decel times, so the motor draws a low amount of current, reducing energy consumption and associated belt wear. On the other hand, some industrial applications require fast response, which calls for very short accel and decel times. Built-in motor protection eliminates the need for external motor protection. In variable torque applications, savings can be seen due to the affinity laws. A small reduction in speed can lead to a dramatic decrease in power usage. We can generate torque at zero speed to hold or lock the rotor, a feature previously limited to servos and mechanical brakes. On the other side of the table, we can now overspeed and run at speeds above 60 Hz, provided the motor is able to accommodate that speed. Remote monitor control means that you can monitor and control the system from your desk or from anywhere in the world where you have an internet connection. We are now going to explain how this device actually works. Now, as we go through each component, we'll explain what it's doing and how. Together, the components make a three-phase electric motor turn and produce usable work. The three major drive components are control, power, and the main circuit. We'll start with control. For most drives, the operator uses a digital keypad to program the unit for the given application, and in some cases, to operate the drive locally via the keypad. Things like overloads, accel and decel rates, minimum and maximum speed, and many other parameters can all be set through the keypad. For a user looking for some more advanced setups, there are option cards that can be added which include communication options, feedback encoders, and extended inputs and outputs. For controlling purposes, the user can wire into the digital inputs and outputs and analog inputs and outputs. The I/O terminals also support some communication protocols. Finally, we get to the control board. Now think of this like the brain for the drive. It takes information from the user and drive components and relays the given information or tasks to appropriate areas as required. Let's look at the selectable control methods the drive comes with. These different methods are programmed via the operator into the control board. Depending on your applications and needs, you will want to choose the control method that best fits your requirements. As we move through each of these methods, control becomes better and better. VF, or voltage by frequency control, is the simplest method. Now, this follows a set pattern, increasing voltage as frequency increases. It's great for fans and pumps. It's also very good for applications that do not need tight speed regulation of the motor. When adding a pulse generator or PG feedback device, the speed regulation becomes tighter and the drive actually knows the speed and direction of the motor. A PG is commonly referred to as an encoder. Open loop vector control is a step up from VF and is great for dynamic motor control and can produce higher torque levels at lower frequencies. This method can also limit torque output. It's great for conveyors and most other general industrial applications. Closed loop vector control uses an encoder or PG to give instantaneous feedback to the drive. This allows the drive to be used in true torque control mode. This is great for winders, rewinders, and web applications. Zero-speed motor control is also possible. Control methods available for PM or permanent magnet motors may also be available. This motor is similar to the induction motor we talked about before, except the rotor now incorporates magnets to create the rotor's magnetic field instead of the typical shorted rotor bars. Moving from the control side deeper into the drive, we find ourselves at the main power board. This separates the high and low voltage areas, converting signal levels to something the control board can read and output to. This is used for monitoring critical areas of the drive as well as controlling them. The main circuit is where all the heavy lifting takes place. The heavy transformations of power. Most drives now use this same main circuit with a three-phase AC incoming source that is converted into DC, then back to simulated AC going to the motor. Let's start by moving our way from left to right, building our drive, and understanding the components along the way. Starting at the input of the drive, the first device that the incoming line will see is the MOVs, or metal oxide varistors. These varistors are in place to take on any incoming voltage transients or spikes, such as switching transients associated with relay and contactor energization and de-energization. When these varistors come into contact with a high spike, they allow the spike to bleed off to another line and travel safely back out to the incoming line, thus suppressing the spike and protecting the more expensive components in the drive. Well, this brings us to the input diodes, or input converter, or commonly known as the rectifier. Most drives today perform a full wave transformation, which means these diodes chop the AC line and create a DC supply. That is the first of the three major components in the drive. The voltage output from the rectifier is then refined by a filter circuit consisting of large capacitors and, in some cases, a DC link choke. In any system using a combination of a rectifier and a filter, capacitors may result in discontinuous current draw. Now, this results in harmonics being reflected back on the incoming line. Yaskawa has a video titled Harmonics that further explains this topic and ways to mitigate harmonics. The components between the rectifier and the filter capacitors comprise a soft charge circuit. When you apply power to the drive, the unit must safely power up. This happens relatively fast, but we must slowly charge the capacitors in the drive. An uncharged capacitor will act like a short if full voltage is applied to it instantly. This is not desirable because the inrush current may be too high for the rectifier and upstream supply components. Therefore, we use a soft charge circuit to slowly charge the capacitors. The soft charge circuit is made up of a contactor and a resistor. Now, the resistor limits the current flowing to the capacitor. After the capacitor charges, the contactor closes and bypasses the resistor. Remember, electricity like most of us, will follow the path of least resistance. Once the DC bus capacitors are charged, they act like a storage tank for the drive. The capacitor stores voltage for the system. These capacitors also have a smoothing effect for rectified power. This smoothing reduces the peaks and valleys of the three-phase incoming power that has been rectified. This reduction in ripple helps reduce the wear on the system as a whole. It's also important to note that the voltage level in the drive has now changed by rectifying AC power. The new DC bus voltage can be calculated using this formula. VDC equals the square root of 2 times the voltage of the incoming AC. We now move to the last major section of the drive, the output, or more specifically, the inverter section. The inverter section of the drive is comprised of IGBTs, which stands for insulated gate bipolar transistors. These work together to produce a simulated three-phase AC waveform to the motor. One IGBT will take power to build the upper part of the wave. Then another IGBT building the lower half of the wave. Now remember, we have a three-phase motor, so typically 3 IGBTs are on at a given time to generate simulated AC voltage waveforms to the motor. These IGBTs have built-in diodes that allow current to flow in the opposite direction of the current flowing through the IGBTs, as may be encountered when turning the IGBTs off or when exposed to regenerative conditions. However, the rectifier blocks the regenerative energy from flowing back onto the line. This is also one reason why you might encounter an overvoltage trip. Yaskawa does offer systems that have the ability to put power back onto the line. These units use different drive topologies that allow for regeneration. After the IGBTs come the DCCTs, or direct current transformers. The DCCTs monitor output current on all three phases going to the motor. This can be used for control and motor protection. Let's explain how these IGBTs work together to build this three-phase power. The IGBTs are controlled using PWM, or a pulse width modulation scheme. The IGBTs are basically switches that work at a very fast rate. Since they are either on or off, the only thing we can change is the amount of time they are on or off. So, to build this waveform at the beginning, we stay on for a very short period of time. Then we increase our on time relative to the base sine wave we are building from. After reaching the peak, we then start to reduce the on time until the 0 point, when another IGBT starts to turn on to create the inverted wave. You will notice that the voltage waveform is almost square, but is happening in the positive and negative regions. And that's because the IGBTs are pulling from the constant DC bus. Voltage reacts very quickly compared to current, which causes this block-type output. The pulses are high in amplitude, but the RMS, or root mean square voltage, appears equivalent to the motor-rated voltage. You will find motors that can handle this PWM-style waveform tend to be labeled inverter duty on the nameplate. Now, the rate at which IGBT's switching occurs is known as the carrier frequency. This switching frequency can be adjusted if need be. Increasing the carrier will result in a cleaner, more sinusoidal current waveform, which in turn will make the motor generate less audible noise. However, this will also make the IGBTs work harder and create more heat within the drive. It may be necessary to derate the output current of the drive to accommodate for the increased carrier frequency. It's interesting to note that the reason a motor is louder when connected to a drive versus across the line is due to this switching frequency. The stator laminations in the motor vibrate, causing this audible noise. Increasing the carrier only brings that vibrating frequency to a level that becomes difficult for us to hear. And this leads to a less audible noise and a quieter motor. Decreasing the carrier will lead to the opposite characteristics. That is, there's more audible noise, but the IGBTs don't have to work as hard. As a result, we have a cooler running drive. You can see how the fundamental output frequency reference in blue reflects onto the actual output via this given carrier frequency. Well, we are finally brought to the output current wave for a given phase. As you can see, this looks sinusoidal. Well, remember that an induction motor is basically an elaborate inductor. And what do inductors mainly care about? That's right, current. Well, the drive is sending the motor a relatively nice and clean sine wave so it can do its job, which is to turn a shaft and produce work. Well, now that we've walked through the inner workings of a variable frequency drive, let's head to the lab and take a look at the outside of the box. You'll find information about each drive on its nameplate. The front cover has information such as the model number and serial number, which you would need if you ever have to contact tech support. You'll also see the voltage class and the amp rating in normal and heavy-duty situations. On the side of the drive, you will see the full nameplate with all ratings and certifications. Depending on the type of environment the system will be exposed to, the drive enclosures will vary. NEMA 1 enclosures are designed for indoor applications and provide protection against finger contact with live electrical components and a limited amount of falling debris. NEMA 12 steps up the protection. It's also designed for indoor applications, and all openings have filters that require regular maintenance. The filters protect against circulating dust, falling dirt, and non-corrosive dripping water. NEMA 4X enclosures are designed both for indoor and outdoor applications and provide a degree of protection against falling rain, hose-directed water, and damage from ice formation. NEMA 4X also provides protection against corrosion. Let's head outside and take a look at a NEMA 3R. NEMA 3R enclosures are designed for outdoor applications. They provide protection against falling rain, sleet, snowballs, and prevent corrosion from the formation of ice on the enclosure. Rain hoods over the ventilation holes prevent rain and insects from entering the cabinet. Yaskawa 3R enclosures also include filters to provide some protection against the ingress of dust and dirt, which is not a requirement for UL or NEMA specifications. And now it's time for your favorite part of our program, the review questions. Number 1, does a motor draw more current when started across the line or when started using a VFD? When starting a motor across the line, there will be an inrush of current. This is due to an instant frequency of 60 Hz applied to the stator at full line voltage, and the rotor must then play catch-up. That in turn causes excessive current draw. The drive has the ability to slowly increase frequency and voltage going to the motor, thus limiting any inrush. Question number 2. What does the acronym MOV stand for? That's right, metal oxide varistor. These help dissipate some high incoming voltage transients that could damage the internal VFD components. Question number 3. Does a drive output a purely sinusoidal AC voltage waveform? No. The drive outputs a simulated AC wave that uses PWM, or pulse width modulation, to build the waveform. And now for our final question. Can a drive be mounted outdoors? Well, of course it can be, if it's enclosed in a NEMA 3R cabinet. A 3R cabinet is made to withstand rain and sleet. Well, this program is just a basic introduction to variable frequency drives, what they do and how they work. There's a lot more to learn, and a good place to do that is at Yaskawa.com. Yaskawa gives you a high standard of product excellence, high mean time between failures, low cost of ownership, quick response to your questions, free technical support 24/7, and a great return on your investment. You get it all from Yaskawa. the world's largest manufacturer of AC drives and motion control products. At Yaskawa, we do everything we do to make each experience with us a great one. Because to us, it's personal.